Hello everyone, this is the lecture on the mathematics of protein design, essentially an overview of the mathematics behind the machine learning algorithms commonly found in some of the protein design pipelines. So let's get started. We begin with a look at probability. It's pretty much fundamental to machine learning. Then from that, we look at some of the basic maths behind machine learning, and then how to represent proteins in these ML frameworks. Then finally, looking at ML in a more abstract sense, using Bayesian statistics and some ways to estimate parameters and parameters in probability distributions. Then there's an example of training a model with PyTorch, which is a machine learning framework. And finally, a conclusion with generative models. So let's begin with the simple Gaussian probability density. Essentially, a probability distribution or density is a function that maps one value to its probability. So here we have one variable, x, and where the curve is high, it represents a greater probability of that value of x happening. So here, what I want to stress intuitively is we have these things called parameters. In the Gaussian distribution, we have two parameters, mu and sigma. Mu is the mean, sigma is the standard deviation. So essentially, parameters of a distribution specify the shape of a distribution. So I think it's helpful to have this picture at the back of your mind whenever you think about a distribution, because eventually, later in the slide, I'll be talking about a distribution over protein sequences. And rather than just having one variable, you're going to have maybe hundreds of variables that can have their own probability. But essentially, you can think of a curve, and if you're sampling from a distribution, you're simply picking out these points on the curve, where the lower that curve is, the less likely for that to happen, and the higher that curve is, the more likely that is to happen. A brief word on expectation and variance. Expectation is simply a weighted sum, where the weights are the probabilities of that value occurring. So here I'm summing over all the possible values of x. That could really represent anything. So for instance, in this example, we're considering a coin toss. So perhaps 0 is heads and 1 is tails. Then suppose it's a fair coin where the likelihood of each heads or tails is 0.5. And here we could just see the expansion of the definition. The variance is all defined by the expectation. It's really the expected difference between your possible values from the expectation of those possible values. So how far away your values are from the center or from the mean. In the Gaussian example, this specifies how distributed or how widespread your events can be. And I'm being very general here because this is really a general framework. X could really represent anything. In this case, it's a discrete number because I have this summation, or it could be a real number. But numbers can represent a lot of objects too. So in this case, we had coin toss, but in our case, we can talk about proteins. Finally, we get to what machine learning is. Essentially, it's an input-output machine with a bunch of computation in between. And the computations are matrix multiplications, which can be thought of as linear operations, followed by these activation functions, which can be thought of as nonlinear functions. So it's a composition of linear plus nonlinear, and all of these functions chained together to get from your input to your output. And it is this modularity of ML models that make it so versatile and customizable to many different applications. For example, I could have the input layer be a protein sequence, and the output layer just be a number. say predicting the brightness of a green fluorescence protein, where the computations are done by these layers. Now let's take a look at what each of these layers, or what these computations mean. So at every node, here represented by a circle, essentially we're looking at 3 edges, or in this case 3 edges, approaching that node, and essentially that outlines the dependence. So suppose we had this first node as x1, this one is x2, and this one is x3. Then suppose we had weights w1, w2, and w3 along these edges. Then the value that's going to be computed at this node is simply a weighted sum. So w1 x1 plus w2 x2 plus w3 x3. These x values are given, so that could be your protein sequence. But these w values, they're learned. So when you say machine learning, essentially you're learning these weights that you're multiplying your inputs by. Usually we can have a bias term. I'll talk about the intuition with that a bit later. In addition, as you may recall, I talked about an activation function. So an activation function, let's just denote it by A for any possible activation function, but it could be a variety. I'll talk a bit about the examples of these later. These are linear layers. I'll talk about why this is considered a linear layer, but essentially you can have at the back of your mind this equation y equals mx plus b, where b is how shifted that curve is, or that line is, and m denotes the slope. In this case, we have 3 inputs, x1, x2, x3. It's just the same thing, but in multivariate case. So we have 3 input values and 3 weights plus a bias. We can organize the model parameters I talked about in the last slide, those weights, into a vector. So in this case, one single neuron, the output at least, can be simply the weighted sum of x1 to x4 if you have 4 inputs. So essentially that can expand into w1 x1 plus ... to all the way to w4 x4. And recall in the previous slide, we had not just one neuron per layer, but you had multiple neurons per layer. So suppose you had 4 output neurons and 3 input neurons, right? This was our first layer in the previous slide. So suppose it's also a fully connected layer, which means all these connections between all the nodes are possible, right? Then you can simplify, so you have many weights, but if you look at this in terms of a matrix multiplication, it becomes a lot easier. Essentially, you're transforming values in 3 nodes to values in 4 nodes. Then essentially it's multiplication by a 4×3 matrix. Right? If you look at the dimensions, it match. So it's 4×3. This one is 3×1. So the output is going to be a 4×1 matrix, or a column vector. The bias here, sometimes this bias, all 4 values are the same, but here, just to be completely general, you can have 4 different bias values. And these h1 to h4 are what the values you have here, h1, h2, h3, and h4. And of course here I didn't have an activation function. So if you had an activation function, you would apply those activation functions element-wise. So then what you would have is the output. If you apply an activation function here, say the sigmoid activation, then it would simply be sigmoid of h1 all the way to sigmoid on h4. And again, that would be organized in a column vector. A brief word on nonlinear activation functions. So simplifying that matrix multiplication and addition in the previous slide, you can write that as wx plus b, where the uppercase w denotes a general matrix, and those lowercase bolds, they denote column vectors. So applying that activation function here, we obtain the final outputs. So the activation function could be one of these. There are many other activations that are possible. The point of activation functions is really to add in the layer of nonlinearity. And you could see the point of that in this demonstration on TensorFlow, where if you try to classify a nonlinear data set with a nonlinear decision boundary, say you had, so in that example, you had the classification of blue dots and orange dots. So if you had the blue dots in the center, sort of distributed in a ball, and you had these orange dots sort of around this, also in a ball, then the decision boundary between these two classes is going to be sort of something like this, right? But that's a circle. You can't specify a circle with simply a linear function. So you need to add some sort of non-linearity in order to make that happen. So you can try this out for yourself. If you don't add in a nonlinear activation, your machine learning model, at least for this particular data set, would fail. Another purpose of these activation functions is to sort of squish values in between a range. So in particular, these two activation functions, the sigmoid squishes values between 0 and 1. And so if you have an output that is passed through a sigmoid layer, that can be interpreted as a probability. You can also squish values between -1 and 1 in the tanh layer. There are some issues with these with regards to how stable your learning can be with respect to gradient descent, but that's for another topic. Now, I mentioned gradient descent. You might have heard this term before. Here I just want to give you sort of an intuition on what the purpose of this is. So in a machine learning model, what you want to do is to tune your parameters. So you can imagine your parameters as like these knobs on a very complex soundboard, or a radio with many different knobs that you have to tune in order to get that signal. So here you have two knobs that you can tune, the north coordinate and the east coordinate. So here, essentially the height denoted by these numbers here is the value at those two coordinates. So for example, if I pick this point, -29 for north and somewhere here for east, then that value at those 2 points, at those two chosen parameter values, is 284. The diagram here shows level curves, which means every single line on this, every single point on this curve has the same value at 284. And this is how like terrain maps are shown. Okay, now the goal of machine learning then is to pick the proper or the optimal parameters such that your model performs the best. And I'll talk about what best means eventually. But suppose, you can think about that as sort of like a local or a global optimum, whether that is the maximum or a minimum of a function, right? Thinking of that abstractly lets you use that all those optimization tools that you know from calculus. So essentially, gradient descent simply is an algorithm to find a local/global optimum. It generally finds the local one, but it may not find the global one with guarantees. Those are, you have to add in some other tricks in order to do that. But in general, let's say we're looking at a maximization problem. So here on this terrain, if you look at this, you start with 283 and you end with 284. So here visually, that's the local maximum. But the algorithm doesn't know this. The computer can't really see this plot. If it wants to see this plot, it would have to evaluate all of these points, right, at all of the possible north and east coordinate values, all of the parameter values, and that's infeasible. We want a way to optimize or find that maximum or minimum in the fastest way possible. So what gradient descent does is, suppose you start off at any point. Let's start off here, for example. We're already pretty close to the local maximum. if you take the gradient of this loss function, so let's call the function dependent on north. So let's call this function L, that's dependent on north coordinate and east coordinate, right? Then you take the gradient of that function. The gradient is a vector of partial derivatives. The gradient function is going to give you a vector. That vector is going to be di-L by di-N, comma di-L by di-E. And it's a vector. So that vector, here we see we have two components. And in our loss landscape, if you visualize that vector, it's going to point in approximately this direction. The property of the gradient is that it points in the direction of steepest increase. And this direction of steepest increase is that direction which is orthogonal to the level curve. Because the level curve is when you're not moving at all, you're at the same elevation. So intuitively, if you go 90 degrees to that direction, you're going to go in the direction of steepest change, in this case, steepest increase. Then the negative gradient will go in the direction of steepest decrease. So if you want to find a maximum, you would go in the direction of the positive gradient. In this case here, that's the negative of the gradient. Intuitively, you can also think of this as how much should I tune our parameters n and e such that you get the maximum effect. And that's why you have these derivative terms. You're looking at how much your loss function changes given some slight perturbations in your parameters, right? Now about these loss functions. I wrote that L for a reason, because it stands for a loss function. In a machine learning situation, you want to minimize your loss. Loss being how inaccurate your model is performing. So suppose we're looking at this regression problem. The regression problem will imply the use of one particular loss function that's suitable for it, which is mean squared error. Essentially, it's measuring the distance between your prediction values and the actual values in your data. So usually we see data represented by script D. In our case, we have pairs of data, protein sequence and protein function. And then we have n of these. So the point of a machine learning algorithm is to have predictions that match those of the target. Let's skip the second point for now. Suppose our machine learning model is this linear model, wx plus b, right? It looks very strikingly similar to mx plus b. That means our y is the predicted values. So we look at the difference between our prediction and our target, the true values for every single data point, and we have n of those. So we sum over all the data points, we divide by n, which is to take the average of all those n points, and each element is squared because you don't want negative values and positive values. You want these to be strictly positive values. So essentially you want to minimize this function, and hopefully, given the intuition on the previous slide, you know that taking the gradient of this function gives the direction of steepest increase. So then the negative gradient is going to give the direction of steepest decrease of the loss function. The second bullet point here really shows the purpose of a machine learning model. It is to have accurate prediction in some new protein that is not in the data set, and you wish to predict its property value. And that brings the notion of generalization, which I'll briefly touch upon later. So for different machine learning tasks, you want to use different loss functions. So previously we saw the mean squared error. Here we're going to see two more. First is cross entropy, and the second one is KL divergence. Cross entropy is used for classification tasks. So in protein classification, for example, you might be wondering, how can we specify a class? So suppose we had K classes. Then, you have different classes of proteins, such as a hydrolase, or for example, a DNA binding protein. and many more. Suppose you had k different protein classes. So to specify a class, you simply assign an index to that class. So suppose you want hydrolase to be assigned index 1, or the first index. Then you put a 1 at the first position, and for every other position, you put a 0. Then for DNA binding protein, suppose you assign it the second index. So that will be 0, 1, and then everything else is going to be 0. Then you have k elements, where only one of those k elements has a 1, everything else is 0. And that is the definition of being one-hot encoded. Right, and this is exactly what this bullet point says. Now, in our loss function, we also see this term y. Y is a vector of probabilities, essentially the predictions of your model. This is a generalization of that sigmoid activation function. Softmax is that term for this multivariable form. So the intuition behind this is that this is going to be the output of your model, Z1 to ZK. So you have k different output neurons, and you pass it through that softmax layer. What it does is that for every single element, here we have k of these elements, for every single element is going to output a value between 0 and 1. And that can be interpreted as a probability. The other important thing is that all of the elements in this vector sum up to 1. So the sum of all the elements in that vector is equal to 1. And that makes it a valid probability distribution. And that means each element can be interpreted as the model's prediction on the likelihood of your input being in that class. So suppose this value was very close to 1 and everything else was close to 0. It's not going to be exactly 1. Say this is 0.98. Then the model is, you can say, is 98% confident that your your input sequence will be of the hydrolase class, for example. And the loss function here is the cross entropy. I'll take a look at the diagram later, but essentially it's the dot product between that true class and your prediction. The second loss function on this slide is the KL divergence. It's a measure of the dissimilarity between two probability distributions. So here we're looking at the dissimilarity between distributions P and Q. And so here, just by looking at the equation, we can see that if those two distributions are exactly the same, then, let me use a different color, then this term is going to be a 1. So log of 1 is going to be 0. And so this whole term is going to be 0. So that's intuitive, right? Two distributions that are the same should be not dissimilar, and hence the divergence is 0. Let's take a look at an intuition behind cross-entropy loss. On the previous slide, we recall cross-entropy loss in the multivariable case was minus t transpose log of y. These are both vectors, so we can expand this in the two-variable case to have t, comma, 1 minus t log of y and 1 minus y. So I can say for sure that it's y and 1 minus y because we know that the sum over that probability vector needs to be 1, right? And t and 1 minus t is simply because we're predicting either t equals to 1 or t equals 0. And we can see that a bit more clearly if we expand this. So let's expand that. Essentially, we get minus t log y minus 1 minus t log of 1 minus y, where t is your true value and y is your prediction. So y can change all the way from 0 to 1. Remember, that's like a probability output of your model. T can be either 0 or 1. It's discrete. So that's why this is pretty convenient, is because when t equals 0, this term goes out. And when t equals to 1, this term goes out. and this term, the other term stays. So it's either the first term or the second term exclusively. So let's consider the case where t is equal to 0. When t is 0, that term is 0. But when t is 0, the second term simply becomes minus log of 1 minus y. And that is exactly this blue curve here. If you think about a log, you have to sort of flip it vertically and also flip it horizontally, because you have this minus and this minus. So when y is approaching 1, this blows up. And you can sort of say, okay, because you're taking a log of 0, right? It naturally, intuitively, it blows up. Why do we desire such a loss function? This is something that it's sort of arbitrary. What loss function you decided to choose, it seems arbitrary, but there's actually a probabilistic background and rationale as to why this is a great loss function to use. But let's look at it slightly more intuitively. If your model prediction is 1 or very close to 1, when your actual prediction should be t equals to 0, that means your model is very wrong. So your loss is very high. That means your model is going to be more severely punished for high confidence on a wrong prediction. So if you weren't that confident, you were say, okay, maybe it's like somewhere around 0.6, then your loss is much lower, right? Exponentially lower. The other intuition in machine learning is that the slope or the gradient of a function can be interpreted as a learning signal, because we're changing our parameters with depending on where the direction of the gradient points. So if our gradient here is very steep, but our gradient here is much shallower. That means in this point, when our model predictions are very wrong, we have a high learning signal. And that makes intuitive sense, because if our model is very wrong, you want that signal to be very high such that your model can improve quickly. But in this case, you have a lower learning signal. And if you're very close to a correct prediction, you don't want your gradients to be, the magnitude of your gradients to be very high, otherwise your learning will be unstable. A brief word on KL divergence. It is not a distance metric, because the KL divergence function is not symmetric. So in mathematics, there are 3 properties that makes a distance function a distance function. And one of them is that being symmetric. So in this case, if you swap the positions of P and Q, these 2 things are in general not equal. So for some implications of that, I include a link down below in the slides. So when you're talking about KL divergence, I think you should be careful in saying that it is a measure of dissimilarity. Right? You can sort of think about it as distance, but it is not strictly a distance function. A trick in machine learning is known as ensembles. And we can have gradient descent, we can optimize our loss function, but really to have a model perform really well, you sort of have to add these additional tricks from our bag of tricks. One of these being ensembles. Essentially, it's averaging our predictions, or taking the majority vote. And it's really saying that I trust the crowd more than I trust in a single prediction function. So in our regression case, we can just take the average of all of these predictions, where hi of x is our prediction, and then you have m different models that are trained independently, and the final prediction is simply the average. So in the classification problem, you can again have m different independently trained models, but then your final classification, you can't really take the average. That would just be like the majority vote of those predicted classes. So here's just some mathematical facts about ensembles. It doesn't actually affect where you predict. So suppose you're throwing targets at a bullseye, right? It doesn't affect where you hit on the bullseye. So suppose you were somewhere here, right? That's where your dots land. But however, it can reduce the variance of where you hit the bullseye. So with ensembles, your predictions might be a whole lot more concentrated. And that reduces the uncertainty in your predictions. But it's not going to change, the correctness of your predictions if they were wrong in the first place. Now let's talk a bit more about model performance. Remember I talked about the loss function. It is how accurate, it's a measure of how accurate your model is. But you don't only want to assess the loss function on the data set that you have, because the ultimate goal of machine learning is to have it generalize to unseen data. And that is the whole virtue of why you want to train a model in the first place. So to assess the ability of it to generalize, what we can do is, suppose this is the data we have total access to, that we can get into our hands, we leave a portion of this data out, and we never let the model see this particular set. So we call the first set our training set, and this is going to be the majority of your data because you want a lot of data to train your model. And for the set that your model doesn't see, this can be called a test set. In some cases, you also have a validation set just to make sure your model is doing things properly and for fine-tuning. But the basic case is that you leave out a test set that your model never sees during training. Then here, what we see with these two curves is that this in blue is going to be our training loss, and the curve in orange is our test loss, or our validation loss. In general, the test loss is going to be higher than our training loss. So what's interesting about this curve, and it could be this case with many others, is that the longer you train, sure, you decrease training loss, but you could sort of see a slight increase in the test loss. And that means it's a sign of overfitting. You're sort of memorizing the intricacies or the data points in your training set, and it's not going to do a great job generalizing to unseen data. So you have to be careful of that. And a very easy way to just prevent that from happening is to stop training early. You don't have to train it for hundreds of epochs if you don't need to, because your validation loss might be increasing actually. Another tool in our bag of tricks is transfer learning. So in many applications, including synthetic biology, you don't have a lot of data. And the problem with that is machine learning really is data hungry and data driven. So how can we learn a generalizable model if we only have very few data points? So an idea, rather than having this existential crisis over machine learning, is first learn your model on a larger data set. That's going to capture some of the more basic features of the data that you're looking at. For example, if you're looking at pictures, looking at a larger data set, perhaps we'll get the first few layers to capture features like edges or curves. And then you can fine-tune parts of that model, or even add additional layers to the end of that model, but keeping some of those weights fixed. And then you fine-tune it for your smaller data set. So one example in natural language processing is BERT, which is a pre-trained model that you can find on the Hugging Face website. Essentially, it's pre-trained on 40 gigabytes of text. And so all of these weights, they're provided to you. You use those weights as the initialization weights for your model. And then for your particular task, you could probably say, okay, I want to maybe fine-tune a subset of these weights. Or in addition, you can add in a few more layers at the end and simply use the output of the larger model for your subsequent smaller smaller application. So this is critical for data sets where you don't have a lot of data. It's the case in protein design because your particular protein is more than likely to not have more than, say, 10 or 15,000 protein sequences. And the scale of data that machine learning algorithms need are usually in the order of millions of data points. So somehow we have to find a clever way to first train our model on, for example, we have a GFP data set that's approximately 56,000 sequences that maps to their brightness values. We can first pre-train our model on these GFP sequences and then transfer some of that knowledge to your particular problem. The caveat behind transfer learning is that you have to be careful and aware of what features you think you're transferring. So in natural language processing, you might be transferring features like sentence composition, or end of sentence structure, sentence structure. But in protein sequences, that's less obvious. You don't really know what features you're transferring over, so again, that might be something you want to look into, because GFP sequences, those proteins fluoresce. So if you're trying to transfer, you use transfer learning for something like enzyme design, you have to be a bit careful in that. So I sort of touched upon this in the last slide, is what features you're sort of transferring over between the larger data set of GFP and your protein sequence data set. That's really not obvious at all if you don't have an interpretable model. So this idea of interpretability is quite important in machine learning, because we don't want to think about our model as just a black box model. That way we don't really know what's going on, right? It's just simply an input to output machine. You give it a protein sequence, it's going to spit out a number, and you don't really know why the model is performing that way, even though it might be very accurate. So essentially, we want to sort of dive deeper into seeing what those individual neurons are doing, if they're doing anything at all interesting that we can, as humans, interpret. So one example of this is looking at the neurons in convolutional neural networks for image processing or computer vision. And what they do is they select a subset of neurons, then they perform gradient ascent rather than descent. So essentially trying to find the input values, in this case these images, trying to find the input values that maximally activate those set of neurons. So you could sort of think of this as neuroscience, right? You have sort of a bunch of neurons that you want to look at in the brain, then you shine images at a mice or mouse, and you see which of those neurons are active. Then you see, to what particular images those neurons are most active. I guess one very interesting example is, there are certain neurons at the back of your eyes that activate when you see edges and different orientations of edges. So I think that's like the V2 or V something system at the back of your eye. So we're trying to do the same thing with neural networks. Finally, we get to proteins. Very basic introduction. A protein is a sequence of amino acids. Each amino acid is represented by a letter. Different from the English alphabet, we have 20 canonical amino acids. There can be more, but naturally we can just consider 20. A protein is stored, at least the structure of a protein is stored in something known as a PDB file. Those things you can find on the database on rcsb.org. Right now we have about over 150,000 different structures on this database, but we have over hundreds of millions of sequences on UniProt. So it's important to realize what kind of data you're working with, because we have much less structural data than we have sequence data. And that's why a lot of the more recent work on protein design is focused on looking at sequence data, just because you have millions of sequences rather than structures. Taking a look at amino acids, they're not just letters of an alphabet. They are these actual chemical structures with chemical properties, and it's important to know what you're dealing with here. So in these amino acids, we have a constant backbone. It's the same for all 20 structures, and we have a variable side chain that's shown in color. That's going to be what's different in those 20 amino acids, and the properties of those side chains dictate the shape and function of a particular protein. So here we have these nonpolar side chains. You can think of these as like oil-like, so they tend to clump together. Here we have polar side chains. These are water-loving, so they tend to be sort of on the surface of a protein. And then you have these interesting charged amino acids, basic and acidic. These can form like the channels in ion channels, allowing charged ions to pass through, and many other interesting functions they can do as well, like catalysis. So how do you represent proteins in a machine learning algorithm? The simplest way to do that is similar to that classification task. We use one-hot encoding. So just to recall, you assign an index for every amino acid letter. For example, you can assign the first index for alanine and so on. Then for an entire protein sequence, suppose you have n amino acids in that sequence, your input value can be represented as a matrix, and it's essentially organizing all of these amino acids as column vectors. So you have, for example, alanine. Oh, the first one should be methionine. I don't know which index that would be, but the first one, I think it should be methionine, right? And then so on. But in your ML algorithms, usually your input is going to be a vector. So what you do is you stack these vectors on top of each other, and then you make a very tall and skinny column vector like this that has, in this case, 20 times n entries, and where the width is 1. That's going to be your very long input to your machine learning algorithm. Another way to represent proteins is as graphs. For this one, you need structured data. So let's take a look at what I mean by a graph. It's a collection of nodes where each node represents an amino acid. Suppose this is alanine, leucine, and another leucine. Well, let's make this aspartate. So it's acidic. These two might interact, and these two might not interact with the acidic one. So what I mean by interact is that they're less than 6 angstroms apart. So we connect two nodes by an edge if they are less than a particular cutoff distance apart. And in an adjacency matrix, we can visualize this. So let's try to visualize this particular graph. Essentially, we have A, L, and D. And we also have A, L, and D. We don't have sort of these self connections. Well, A is obviously less than 6 angstroms apart from A. So I guess you could just say A and A, those have an edge between them, but that's up for debate. They're not really interacting, they're the same thing. But here, A and L, they share an edge. So you put a 1 for both of these entries. But A and D and L and D, they don't have edges. So we put a 0. So that's an adjacency matrix. And in this picture, I show the adjacency matrix of this enzyme PETase. So it's over 250 amino acids in length. But in white, you see the 1s, and in black, you see the 0s. So here, obviously, it's the backbone, this white diagonal. But what's interesting is that you see these white dots that's not along the diagonal. Say this one right here. That's something like the 10th amino acid interacting with 225th amino acid. That's a long-term dependency, right? Something at the beginning of your sequence is interacting with something at the end of your sequence. That's, usually the case in proteins because proteins fold in these complex 3D shapes. You don't know which strand is interacting with which unless you look at the structure. So these graphs, using such matrices, they can encode structural data in sort of this matrix form. So recently there have been developments in using GNNs or graph neural networks to design proteins, where you really essentially it's the same thing. You think of a graph, you think of a protein as a graph, and suppose you don't know the identity of that amino acid, and you want to design, well, you want to know what that identity of that amino acid is for a design problem, then you use a graph neural network, and that neural network is going to make a prediction on what that amino acid there should look like. So that's an interesting application of graphs with proteins. Now we look at Bayes' rule. I had a game for cards that we could have played, but unfortunately due to the situation, I'll just sort of explain to you what I wanted to do. By this picture, you may sort of know what's going on. It's a black 5 of hearts. That's not supposed to be the case in a normal set of cards. It should be red. But what I want to stress with this example is this notion of a prior. So we have all of us who have seen cards, this prior that hearts should be red. So when we see evidence that suggests otherwise, we might change our perception. We might change our conception of what the world looks like based on that new evidence. But the tendency of that change really depends on how strong our prior is. So I don't know, if you played cards for your entire life and you've only seen these normal cards and not any of these anomalous cards, then you might be inclined to seeing just a red 5 of hearts, even though you see a black 5 of hearts, i.e. you're rejecting the evidence that you're seeing. So your prior is this term in Bayes' rule, and that's your posterior. The likelihood and evidence, those are the things that you observe. That's the data you observe in real life. So in the demo, I wanted to give you some likelihoods and evidence and to see how fast you can update your prior into the posterior. This is quite interesting. You can look at that. You can look up this experiment here. What they found is that some people, they really never got that they were seeing a black 5 of hearts, and this has ties to actually scientific discovery, where if scientists have a very strong prior in that, well, i.e. they really believe in what they're doing already according to the literature and according to their own experience, then when they see new data that's anomalous, that doesn't really fit with their theories, it depends on how strong that prior is. They may reject it or they may accept it. So this Bayes' rule thing, is generalizable to even scientific revolutions. As I mentioned in the last slide, here we just see a graphical representation of what a weak versus strong prior means. So here on the left, we see a weak prior. And so the likelihood is going to dominate the posterior. Our posterior is very close to the evidence or the data that you observe. In this case where you have a strong prior, even though you observed evidence that is much different than what your prior belief is, your posterior, your updated belief isn't that much different than what you previously believed in, even though it did shift a bit in the evidence. Now let's change gears a little bit and think about machine learning algorithms and neural networks from a probabilistic perspective. So suppose we store all our parameters of our neural network in this vector theta. That can be thought of as the hypothesis of your neural network landscape. So for example, in our protein sequence to function prediction neural network, essentially theta is our current belief of what that sequence to function landscape should look like. Here, the likelihood is simply, given that hypothesis, what is the probability of observing new data given that hypothesis, right? In this case, new data would be in the form of new data points. So a new sequence to function pair. In this case, I'm just writing in the most general sense. You could have a whole bunch of data, right? So this is the likelihood function. We would like to maximize that function because then we would have, more ideally, we would have a hypothesis that under which the observed data is the most likely, which you can think of as this is the correct hypothesis, or the hypothesis that best explains our data. So in the Gaussian distribution example, many slides ago, suppose our hypothesis, our theta, those parameters drew out a Gaussian distribution that's very flat like this. And then we observe data. We observe data that's concentrated on around here. So we observe many different data points, and we have many points that concentrated here, but very few elsewhere. So clearly this particular, our original conception of the ideal parameters or the hypothesis needs to be updated, and that's incorrect. So we would like to shift our hypothesis to those parameters which generate a curve that best explains our data. Okay, just a little bit of caveat or a little bit of technical details. You usually work with a negative log because taking the probability of multiple data points, you're essentially multiplying them together, and that term can easily vanish to 0 because probabilities are between 0 and 1. So if you take the negative log, that stabilizes that number, and you solve for that those optimal parameters with either gradient descent or solving it directly by setting the partial derivatives to 0. The MAP estimate is similar to the MLE estimate, the maximum likelihood estimate, in that it also contains this likelihood term, but it contains our prior as well. So let's walk through the derivation. MAP estimate stands for maximum a posteriori estimate. So as suggested by the name, it essentially tries to maximize our posterior. Given the data, I want to maximize over possible parameter space, again, this posterior. And the intuition behind this is that this allows you to place a prior on your parameter space. So here, you could say that I've only seen cars, hearts that were red. So here you could specify a prior. Okay, but let's walk over the definition or the derivation. So probability of theta given d, let's just plug it into the definition. That's theta and d over probability of d. But here you're only taking, you only care about the maximum value, the argument of that which gives you the maximum, and the denominator is independent of theta. So we can just simply drop that out of the maximization problem. That gives you the second line. Okay, the second line to the third line, well, P of d given theta is P of theta and d over P of theta. That's equal to P of d given theta. Multiplying it to this side, we get the equivalence. And here, I'm taking a log. Why, Why are these two terms equivalent? Well, because taking the log doesn't actually change where the maximum is. You're still taking the maximum, you're still trying to find the maximum over theta. Taking a log doesn't change where that theta is. And again, similar to what I said on the last slide, you take the log to stabilize these terms. Okay. Here, just a reminder of where all these terms are coming from. We have a lot of different notation. So this is our posterior. So given the data, let's update our prior. Let's update our distribution over parameters. So yes, let's update our prior. This is our prior belief on what the hypothesis of what we observe should look like. And this is our likelihood. The likelihood of observing data given our hypothesis, encoded in theta. Okay, so those are just in words of what I talked about down below. Finally, we get to using Bayes' rule in protein design. And this is at the core of this algorithm CBAS written by David Brooks. So conditioning by adaptive sampling, otherwise known as, well, short form CBAS. Okay, let's look at the notation. We're going to let X be a vector of length L. Each element is a natural number that represents a protein. So that represents an amino acid. So in our case, each amino acid, one of 20 amino acids, each element is an integer from 1 to 20. Okay, then this is where things get interesting. We're going to let S be the set of desired property values. This could be anything, right? It could be brightness of a protein. It could be catalytic activity. It could be, rate of secretion. So many different things you can think about. Essentially, any property works. And that is the magic of machine learning. And that is so generalizable to all of these different properties. In classical protein design, you have very limited, everything is focused around this energy landscape of looking at the thermodynamics or the stability of a protein complex. And then you have to sort of apply that to look at the function of a protein, which can be very difficult. In this case, you can specify any arbitrary property. Okay, so this is just the definition of what P of S given X means. So given that protein sequence, we already know what that protein sequence is. What is the distribution over the property of values of that sequence? So essentially here, that is essentially what I said. And P of S given X, since S is a set, we're going to integrate over all the property values and only include those that fall into that set S. So this is an indicator function where it's 1 if y is in S and it's 0 otherwise. So this particular term is only added to that integral if your property value falls into the desired set S. So then to model a protein, to design a protein, we're going to model this distribution. Okay, let's take a look at what that means. Given our desired set S, and given the parameters of our model, we're going to find a distribution over protein sequences X. And that's going to be our optimal protein sequence distribution, from which we can sample and generate these optimal protein sequences. So we apply Bayes' rule. Okay, after applying Bayes' rule, this is what we obtain. We see we have these two parts. The first part is our sequence to function model. So given a protein sequence X, let's find if that X actually has a property value that belongs in our optimal set S, right? P of S given X, exactly this definition here. The second term is our generative model. We're given theta, which are the parameters, which then, as you recall, we can think of as the hypothesis. So i.e., it encodes what we know about the protein sequence space of our particular protein or of all proteins in general, depending on what training set you have. So that encodes the knowledge you have about what possible mutations there can be and what proteins are stable. Then you're going to generate X. And I use the word generate because it's a probability distribution over X from which you can sample. So this is your generative model. Okay, there it is. You can have a sequence to function model parameterized by a neural network. You can have a generative model also parameterized by a neural network. But it's not that simple. The problem with that is our denominator. So the denominator, what does it mean? Let's take a look at that on the next slide. The denominator intuitively means I want to sum over all possible protein sequences because the integral is over dx and x represents a protein sequence. So the denominator is totally not tractable. It is not computationally feasible to compute this denominator explicitly. So we can work our way around that by estimating this distribution by a proxy distribution, and we sort of push that proxy as close as we can to our target by measuring the dissimilarity between our target and a proxy, which we can evaluate using the KL divergence. So we simply minimize that dissimilarity by taking the minimum of our KL divergence, finding the particular parameters of our proxy distribution, Q, such that the KL divergence is minimized. And exactly that's what it says. Then those particular parameters that minimize the divergence, we say those are the optimal parameters, theta star or phi star, that effectively Q is close enough to P that we can sample from this and generate optimal protein sequences. Remember in Bayes' rule we had those two components. One was the sequence to function model, the other one was the generative model. So here is just a look at what a sequence to function model looks like. Unfortunately on YouTube I can't play this video in the presentation, but you can search this video up on YouTube for yourself. It's essentially looking at the sequence to function landscape of the green fluorescence protein. And this landscape, or the shape of this landscape, is what we want our sequence to function model to approximate. Where given some protein sequence, we wanted to predict, for example, in this case, the brightness of that sequence. I also have a link to a Colab notebook where you can actually train a GFP sequence to function model for yourself, all the way from parsing the data, loading the data, and evaluating the model. So the full pipeline written in PyTorch. The second part was the generative model. You actually have a lot of options for this model, similar to the sequence to function model. The one they use in the paper is the variational autoencoder, which I'll briefly talk about on the next few slides. But there are many, many more. So recurrent neural networks, RNNs, these invertible generative models, normalizing flows, and more recently, graph neural networks. So remember I talked about how you can represent proteins as graphs. Well, in this paper, what they do is to generate graphs. So essentially, if you can generate graphs that preserve some of the edge and node properties that you can measure in graphs, then perhaps you can use this to generate proteins. The variational autoencoder is the generative model that they used. I included these slides just for completeness, but it's completely optional if you want to listen or not. But I think it's really interesting how this works. First, let's talk about autoencoders. Scratch the term variational. Autoencoders is a generative model where you have your input data, let's call that X. You're going to encode it into a latent representation, let's call that Z. Then you're going to decode it into your output. Your output is going to be X hat, which is the reconstruction of your input data X. So this might be a bit bizarre. Why are you trying to reconstruct the input data? Well, because you want to generate your input data. But why can't you just have an identity map, right? Why can't you just say, oh, let's just put an identity matrix everywhere? Because you're putting this through a very small bottleneck. In general, this dimensionality of layer Z, of this latent space, is going to be much smaller than that of your input layer. So essentially, it compresses information and it forces the model to capture the more important information in that high dimensional space, compress that into a lower dimensional space from which you can generate your original data with high fidelity. And that's what an autoencoder does. This is the process you do in training, but in testing or in actually using it for generating images, what you do is you take out the encoder part and you only keep the decoder. You sample random numbers from some distribution as input or input noise to your latent layer, or you can choose certain latent vectors. Then essentially the decoder decodes that latent code into images, or in this case, our first example, we're generating handwritten images. There are other examples where we can generate actually these high resolution images of faces. So this is our goal, to approximate this function map from our latent code to our data space. This is what this second bullet point says. We want a function that maps from our latent space to our data space. We also have the parameters of our model in theta space. Now we're taking a look at this variational part. Here we're dealing with probability. So essentially we want to find the optimal parameters that maximize the likelihood of our data, because the ultimate goal that you want from your generative model is to sample from your original data distribution, i.e. you want to model P of X, the distribution over your input data. By the law of total probability, you can take the integral over some other term, in this case our latent variable. You integrate over that and you get this expression. The problem with this particular construction is that not only is it sort of intractable if your latent space is somewhat large, well, it doesn't have to be very large. You're taking an integral over all the possible latent codes. That's intractable, and also the first term is going to be close to zero or zero for most values of Z. Because if you think about it in the protein case, you have some latent codes and you want those codes to map to protein sequences. But it's probably the case that a large majority of those codes are going to map into dysfunctional or proteins that don't stably fold. And only a very small fraction of those latent codes actually mean anything and translate into functional protein structures. So how do we get around that problem? To fix that problem, we take a look at this first bullet point where we have sort of this intuition that ideally you want to pick the latent codes that are more likely to generate valid protein sequences or valid handwritten images in that previous example. So we can model that distribution with Q of Z given X. So given your input data, you want to find the distribution over the latent codes that ideally can map to functional protein sequences or that map to realistic looking images. So after many steps in derivation, details which you can see in this tutorial on VAEs, you essentially reach this objective. So this is what you want to maximize. We have two terms on the right-hand side. Maximizing this essentially serves as a proxy of maximizing the log of your likelihood, P of X, the likelihood of modeling your input data. So essentially the first term, you're sampling Z from this optimal distribution Q. You give Z to your distribution P and you decode it, right? You generate your data from that latent code. So here we could say that P decodes Z to reconstruct X. Here, the second term is the KL divergence. So script D here means DKL. This is the KL divergence between your latent code distribution, your optimal latent code distribution versus your original latent code distribution. So this is to prevent your optimal distribution of Z to be that far away from your original distribution. I say you want to minimize the second term because you have a minus sign. So your right-hand side, the right-hand side of this equation, is going to be maximized when the likelihood of this is, the value of this is maximized, i.e. you have the Z, which gives you a very, data point X with high probability, and with those that minimize the second term. So a very small second term, which is minimum KL divergence between this proxy Q and the original distribution P. So there are some caveats for implementing a VAE for generating protein sequences. So as you know, protein sequences are discrete. Similar to, like, if you use one hot encoding, that's definitely discrete data. So if you want to know how to implement that VAE for discrete data, take a look at CBAS. There are comments in the code. There is also a blog post, which I'll have the link down in the comments, which shows you explicitly how to implement VAEs for discrete data.